Okay, good morning. Okay, from last week courses, is there any questions? I think so far so good. I think last week we have these questions, right? Find the concavity, find the intervals when concave upwards, right? So we start by taking each of this, derive with respect to t. Okay, and then dy dx is so we have 1 plus 1 over t. Okay, good, thank you. 1 minus 1 over t. So this will be t plus 1 and t minus 1, right? And then do the same thing with the second derivative. Remember, we are going to use this formulation. So we are going to first derive the dy over dx. So we are using the quotient rule directly. So this will be t minus 1 squared. And then t minus 1 minus t plus 1, right? And dx over dt is t minus 1 over t, okay? So we are going to simplify. This is cancelled. This will be negative 2, right? So negative 2 multiplied with t is negative 2t over t minus 1 cube. Okay. Now the concave upwards, you remember, this is when the second derivative is positive. So it need to be greater than 0. Okay. So of course, the first thing comes in mind is what the number. So as I mentioned, you take the line number and put all the possibility. Okay. Of course, if you see the denominator, this t minus 1, so t minus 1 supposed to be not 0, right? So we are going to have 1, okay? And what's the other point? The other point is, of course, the 0 itself, okay? Because these equations can be equal to 0, right? T can be equal to 0, and we want to make it greater than 0. We need to make it positive. So the other number or the point is 0. Or you could think like, whenever you find the second derivative, you could always taking this equations equaling it to 0, which means if there is something that is equal to 0, perhaps that is the inflection point, okay? As if you remember calculus 1, okay? But then we need to make sure that our line numbers is positive. We need to make sure that this is going to be positive. So the one that makes the equation positive is going to be in this area, right? If you take all the numbers, because it's a cube, right? It's a cube. Whatever point you put in and that makes negative, and you take the power of 3, it will be negative, right? It will be positive, because negative, negative will become positive. So whenever we have something less than 1, which is in this area, that makes negative, right? And negative, negative become positive, okay? So that's why this is true. If you take the negative here, maybe this will be true, but for the top equation, that become positive. Positive, negative become negative. Okay, so negative, negative. So the only range that is on the positive range is from 0 to 1. Okay, but not including 0 and 1. Or so concave upwards when the interval is that. Okay, just a few notes from last week. So my plan today is just a short review on the polar coordinates, the polar curves, and then go to the calculus in polar. Okay. So I hope the videos that I gave you last week, you have watched the videos, and I assume you watched the videos. So I just make some review, and we can have more discussion on calculus part. And how about your TA? Do you attend your TA class? How about it now? Okay. But they will have like small quiz every 2 or 3 weeks, maybe 2 weeks or 3 weeks, right? Yeah. So they will review, and then the next week after that they will give you some small quiz just to check your exercise. I think that is important for you to have like a small test like that, because sometimes if I give you like, oh, you need to do this exercise, I'm pretty sure that not all students will do the exercise. Unless you are confident and have ability to and have skills so that to some points, I think that's still okay. You can skip that one. You don't need exercise. But if you're still confused or maybe not really familiar into how to develop the formula, blah blah blah, I think you need to at least take the exercise practice. One way to learn, one way to study is, I think every teacher will give you like, you need to be focused, blah blah blah. But focus, okay, if I want to elaborate focus means you are mindful of your surroundings, which means that you are in experience, you are getting used to something, which means you are going to practice out by yourself, okay? Which means you are focused on something. Your mind is going to do that. If you are not really focused, maybe you're just writing all the notes and without even understand what you're writing, and that's dangerous. That's dangerous. So as long as you write notes, I hope you can get focused and you know what you write. You know what you write. And if you maybe somehow, why this maybe why this text looks like this, why this formula looks like this, and that's when you are thinking. It means you are learning something. And you learn something from which you are not aware of. Maybe I don't know about this. So you need to learn about that. Maybe looking some part that you are missing out. Maybe the teacher gives you something and maybe some part of it that's supposed to be given before, but you seems maybe I miss out something. Then you need to review, or maybe you need to recheck, okay, your notes and everything. Okay. Okay, this is just the review on the last week, the parametric curves, calculus on parametrics. Okay. Okay, the next one, I hope everyone finished their notes, is the polar coordinate system. So we first begin with the polar coordinates. I will be very brief on this part because I believe you should be familiar with this. So what polar coordinates means is we are not dealing with the Cartesian. So remember, what we have before is Cartesian, which is the x and y, right? It's x, y. And how the Cartesian develop, if you put points, you will see that you can imagine this is like a rectangular shape. You can make a rectangular shape through all the points, right? And if you have like a books that has a rectangular pattern, this Cartesian perfectly fits with that books, right? Okay. So I hope that's clear. I think when you are in elementary school, you have like books like that have a rectangular shape, usually to write the text or maybe to draw something. Okay. But now in polar, we are not dealing with the x and y. We are dealing with the polar. To give you a visual, the polars means give you like this is an axis, but it's not x and y, okay? And we are just focusing on what we call the polar axis here. Let's say this is a polar axis. I'm not sure whether there are books that is having this pattern, but the pattern will be maybe just like a circle, small circle, another circle. And from this pattern, we know that, okay, we can take maybe here with radius of the circle, and then moving out for some angle here, or okay, we have this point, and all the points will be moving in manners of radius and angles, okay? So that's why we will focus on this radius angles like that. Okay, and if you see from this polar, this is radius, is positive radius, right? So if we moving like and we move like counterclockwise from the polar axis here. So we move positive angle, okay, and then going back to the original point at the polar axis. But if you see, the radius is always positive, right? Just a quick reminder. What if you have a negative radius? Can you have a negative radius?
Different direction?
Yes, different direction. Essentially, you cannot have, but you can try to make out what is the negative radius. It is actually going to be here, the opposite sides of that radius, okay? So if maybe I move this a little bit, maybe make it smaller a little bit and make it here. So this will be the negative r and theta. And of course this will be true when you imagine that it has an additional angle that is theta plus pi. So it can be r negative r theta, or it can be r and theta plus pi. These two coordinates is the same thing. Okay? These two are the same thing. Okay? So they have the same position. And then, still on this coordinates, if you put these polar coordinates, these relations r, theta, into the xy coordinates, you can transform, or you can convert. Okay, you can convert. So conversion. I think just with a simple triangle, you could simply get the x is r cosine theta, and y is r sine theta, and tangent theta is y over x, and you can get these circle equations. Okay, so for all these four formula, you could convert Cartesian polar Cartesians. But if you would like to draw the triangle, let me draw for you. Okay, now after we get this conversion and we know the polar coordinates, now we can draw the polar curves. The polar curves, in general formula, is just we write as r equal a function of theta, okay? Or maybe in more general, we can write function r theta equals 0. So this is going to consist of all the points in the polar coordinates that has at least one representation of the function, and it satisfies the equations. For example, if the equations is r equal to, okay, r equal to, which means if you take a look at the polar, what we have in polar, if we have a radius 2, okay, like a constant, which means we have a circle with radius 2, right? Okay, we have a circle with radius 2 because it doesn't really necessarily have a variable in angle, so which means that it will be going to circling around. Okay? So we could take that as, if we take this is what this looks like. So this is very basic. Okay. So this is r equal to, so we just draw a circle right now. Okay. What happens if you have the constant is the angle? You have line, okay? Line, maybe angle should have a line through there. Okay. Maybe if you have a theta pi over 4, for example, then theta pi over 4. Okay, now what we have here is r equal to cosine theta. Well, perhaps before we draw like the right picture here, we could try to make a table, okay, and try to look on the value, okay, from 0 to maybe some until pi, and we could just focus on the special value, the special angle. So 0, pi over 6, pi over 4, and this is the polar curve 2 cosine theta. Okay, so 0 is 2, pi over 6, so it's pi over 3, pi over 6, sorry, pi over 6 is half square root of 3, so it's divided by 2, it becomes square root of 3, and so on. As you can see, all the numbers here. Okay. And as you mentioned, the value, this part is positive and this will be negative. Which means when you put into a picture, this will be the opposite sides. Okay? So if we look at how we are going to take that, okay, and this will be how it looks like. Okay? So we start from 0, 0 here, 0, and radius is 2, and move. So we start from here. This is the first point. Every time you draw polar, start from the polar axis, and then adding the angle. Okay, adding the angle pi over 6, square root of 3, and perhaps if you draw with paper, you could maybe assume the length. Okay, how far the square root of 3 when we put that point and that point, but because it will be symmetrical, this point, like the positive one, it will be the same as the negative one, right? The length. And then you can have this. And remember, when you have the negative, as I mentioned before, this can practically the same as the positive, but the angle is plus pi. So we can imagine this is plus pi, or this will be 11 over 6 pi, right? And the same thing for the other negative radius as well. Okay. So if I make this the second statement here, it will be make sense for the point itself. Okay. But I hope you can get familiar with the negative one. Okay. The negative one is just saying that, okay, it's supposed to be there, but it's supposed to be the opposite side, and this will be the point. I hope you get my points. Okay, so we move here, and when we have in this exact position here, this is pi over 2, right? But pi over 2 in cosine is 0. That's why it's going to be 0 here. But after pi over 2, we have another angle. What's pi over 2? It's 2 pi over 3. Where is 2 pi over 3? It's supposed to be in somewhere in between this pi over 2 and pi, right? So it's supposed to be here, but it's negative. That's why it's going to be here. Okay, I hope everyone gets the idea. Okay. We haven't yet go to the calculus part. Okay. Okay. Now, if you can think, okay, this is for cosine. So when you have a sine, which sine is complementary of cosine, you will get the similar circle but different position. So this is for cosine. So if you have, for example, if you have r 2 sine theta. Okay. You could try the same thing, make a table, take special value for each angle, evaluate, and then put into the system, put into the polar system. What you get is, you will get this. Let me just take this, the conclusions. You will get this. Because when sine is 0, it's perfectly 0 here. So this is for 0. And then you can pinpoint some, maybe here, the pi over 3, pi over 6, pi over 3, pi over 4, maybe pi over 4 around here, and then pi over 2. Pi over 2 is, the sine is maximum, right? The sine is maximum. This is 2, right? This is 2 pi over 2. And you can pinpoint for every point, okay? But this will be the sine. The takeaway is the maximum point. The maximum point is for cosine 0, for sine is pi over 2 here. Okay? And every time you see sine or cosine in the polar curves, sine will be on the top position like this, and cosine will be here. Okay? And it will be applied in every polar curve pattern. Not only this, but when you plus with something, but it's still in sine, maybe plus with constant, it's still applied the same pattern. Sine is going to the top, cosine going to the right. Okay? Okay, another type of polar, aside from the circle, okay, is what we call the limason, or we call the cardioid. Okay. Let's say we want to sketch the R1 plus sine theta. One way we are going to sketch this is we plot the points. Very similar. Plot the points, take special angles. Okay, and you know all the value for the R. And after that, put into the polar curves. Okay. And this is how the cardioid will be. So start with the first one here. Take the theta equals 0. 0 sine 0 is 0, so it's just R equal 1. So this will be starting from here, 1. Okay. And then take theta pi over 2, which is the maximum for sine. Sine pi over 2 is 1, 1 plus 1 is 2, so it's going to be 2. And how do we know this part and make sure? We can know from each value for each special angle. Okay? And then do the same thing from pi over 2 until pi, like previous circle, and you will get like this. Okay? And exactly this pi is on this polar axis, right? And then take this theta 3 over 2 pi, which is going to be in this 0 here. It's going to be 0. And then from this 3 over 2 pi up until 2 pi, it's going to be back into the original position. Okay? And it's going to be like this. This is what we call the cardioid. It's like a cardioid, like heart. So we call this a cardioid. And remember, this is sine, right? As I mentioned, sine is on the top, right? So its large portion is on the top, okay? But what you need to figure it out is relations, okay? So 1 plus sine, okay? If we could take some constant, let's say this is A, this is B. This is the constant, A and B is the same, 1 constant, okay? So whenever you have that constant, the same, that precisely to be cardioid. So we will have a pattern, Okay. Of course, if A is not equal B, for like maybe let me write here. So R, it can be A plus minus B sine theta, or R A plus minus B cosine theta. Cardioid is if A equal B. What's happened if I take 1 minus sine? What will happen to the curve? Maybe let's go a little bit, go back here. This is cosine, this is sine, both positive. If negative, the cosine becomes here, the sine becomes here. Okay? So let me, just a quick notes. This is if R is negative cosine theta. And this is R negative sine theta. Okay. So this is what was to really happen when you have the negative, right? So the same thing applied for the cardioid and other polar curve as well. Whenever you have a negative part of it, for example this one, so we have 1 plus sine. If we want to make it 1 minus sine, then the curve will be that's curve. 1 minus sine. Okay. And what happens when you have 1 plus cosine? Go to the right. 1 minus cosine, go to the left. Easy, right? You will get used to it. There are other, like other polar curves, a typical polar curve, like rose, like flowers, and the lemniscate. But I will just get you to the conclusions, and please check out the videos on the polar that I gave you. Or if you find other source as well, that's also okay. But whenever you, well, sometimes if you like not really get into the pattern, maybe you didn't remember. One way to draw or to sketch is by the table and pinpoints all the numbers. I think you focus on the first thing. Focus on this 4 value. So 0, pi over 2, pi, 3 over 2 pi. And if you want to really confirm, you can make sure maybe 5/4, okay? Or even 5/3, 5/6 if you want to make sure the points. But I think as a starter, this 4 angle I think should be enough as a starter. Okay, the conclusions or the table for you to know that we have all these polars. So like for a circle we move and make it into sine, cosine, and then we can also make a spiral. So that's when the constant multiplied with the theta. And then we have, so this is what we have before, when A is equal B, right? When A equal B is cardioid. When A is less than B, it's going to be having a loop, okay? Having a loop. Okay. You could try. This loop is when they reach this point, because for one calculations there will be a 0, then you will, the next part of the angle is going to be here, and then eventually start passing through here and goes there. And then when A is greater B, maybe not really that much different, it goes a little bit away from the original point here, but just a little bit. We call this dimple-Limassol. And then when it's greater, equal twice of B, it's becoming convex Limassol. It's like a circle, but not really precisely a circle. It's almost a circle. You can say almost a circle. Okay, this is the Limassol. I'm not sure what does that mean. It's Spanish or no? Spanish or no? Okay, maybe French? I'm not sure. I haven't checked. Maybe I will check. And then rose. The rose curve is R equal A sine or cosine and theta. Okay. And how we draw, it depends on the n. Okay. If n is odd, then we are going to have the number of leaf is just n. But if it is even, then we will multiply it up to n. Okay. So for example, this is cosine 4. Now we have 1, 2, 3, 4, 5, 6, 7, 8. 8 leaves, okay, 2n. But when we have the odd, like 3, this is just 3. Okay. We have 2, it's 4. Okay. 4 leaves. If you want to check, you can check, look other sources, how to make this 4 leaf rows. Okay. This is all for cosine. For sine, the starter will be different. The sine to theta will be here, there, there, and there. That's for sine. But how the sine develop is particularly there will be similarly with the cosine part. The last part is what we call the Leibniz scale. Okay. Not much information about Leibniz scale, aside from when you have this r squared, a squared sine to theta, you will have this like an infinity symbol, but it's going to like that. And the counterpart is just changing sine into cosine, and it's going to be horizontally. Okay. That's what we call the Leibniz scale. Okay. So that is all the figures that popular okay, commonly popular on the polar curves. I think if you watch the video that I gave you, I think the third videos, you'll be able to draw really easy. Okay. But if you have like, you can identify the pattern now. I think that's good. That's good. Okay. Okay. Any questions before? So this is all the introduction of the polar. Okay. The polar system, the polar curves. So everything includes later in the calculus. We are going to change from the Cartesian perspective to polar. For example, if we may be familiar with the integrations in the xy, like the top, the down, now it's in polar. It means that the area will be depends like the integration from angle to angle. Okay. Okay. Okay, if there's no question, let's start the calculus in polar. Oh. Well, maybe not this part. We start from the simple one. Okay, so let me write first calculus in polar. We start from the sector. So if we take some part of circle, like a slice of pizza, right? And we can develop the area of this sector as half r squared theta, right? Now this area of sector will be really important for our approach to the calculus in polar. Okay, and if you forget this area, okay, remember this is just a part of the circle. The circle area is pi r squared, right? And this sector is ratio theta over 2 pi, right? So this will be going over there, right? So this will be a circle. This is the ratio of the theta. Now we are going to use this approach, half r squared theta, and we remember that the radius, as in the polar system, is a function of theta. Okay? So we could imagine like the polar curves can be written also in this equation. So when we are going to evaluate the area, like in the integral, we are going to use this approach. Right? Okay, now look at this. We have some random region Yeah, random region, and we can develop. So this is just a random curve like that, and we can develop the polar curves r equal f of theta function theta. And look at this. We have the theta from A to theta B. Okay, so this region is on this polar curves from A to B. Okay. Okay, I think we can take a break. Okay, we can take a break. Okay, if you check my plan, original plan, this week's supposed to be we have a quiz, but our quiz probably next week. Okay, next week. Do you want Wednesday or Thursday? Thursday, right? Thursday next week. Next week Thursday. So the content, I'm trying to finish all the calculus in polar within this week and give you exercise, also the lecture notes. So next Wednesday we can have a small review and then a little bit introduction to chapter 11, but the Thursday quiz and then continue chapter 11. Okay. Okay, now if we back to this polar, okay. Now we have this region and we would like to know the area on this region R. Okay. And of course, we need to establish the some assumption that the functions for this polar is a positive function. And the range is from 0 to 2 pi for the angles. And to begin with, we are going to start with defining all the region. So we are going to define and we are going to evaluate this small region. Okay. So we are going to approach the angle here is the delta. Just to note that it will be really small. And then let's say we have a function of theta I, which means that's the sample points that we are going to approach. So from the area of the sector, we are going to approach this small area. So it approximately this will equal to okay. And then as you may see that these approximations, we are going to take this into our summations. So the total area is the summation of these formulations. And then we can take the limit concept to connect with the integral as n approach infinity. And then if we take the endpoints from A to B, this is simply the formulations for the area under the curve. So we could take the area. Let me copy one here. So the area area of the polar region. Or we can write in a simple way. A is just integration from a to b half r squared d theta, with r is function of the. But the difficulty of the polar in calculus is not this formula. This formula easy to calculate. The difficulty is to know the A and B. Okay? Sometimes that's the difficulty. And then sometimes we need to decide which R we need to compute. If they are, for example, have an intersection, we need to find the area of the intersection. That's if you know how, it will be, I think you can see the pattern, but if not, then it will be very challenging. And then the other difficulty is you need to change your perspective from Cartesian to polar. That's sometimes difficult. Okay. Okay, I think we can look on, I think, example. Okay. So example, as mentioned here, there is a r cosine 2 theta, and there's a blue region. Okay, so let's find the area enclosed by one loop of the rows r equal cosine 2 theta. Okay. If the question doesn't give you the picture, then you need to draw first. You need to draw the cosine 2 theta. And then you need to find the a and b, right? The endpoints of your integral, the sector integral, right? So from the rose curve, okay, do you know how to start to draw this? We start from here, okay? Because it's cosine, so 0 will be 1, so start from here. And when pi over 2 is or pi over 4, here pi over 4, it's pi over 2, it's 0, right? So when theta pi over 4, when theta pi over 4, r becomes 0. So that's why we move pi over 4, or we stop here, okay? And what's happened when pi over 2? Pi over 2 is cosine pi. What is cosine pi? Negative 1, right? Okay, remember, usually this is pi over 2, right? But because it's negative, it goes through, okay? And do the same thing with all the other points. And then you will get exactly, when negative pi over 4, you will get, goes back to this one, the 0 radius. And then the last point will be getting back to this point, this original point. So we have negative pi over 4 and pi over 4, okay, for the one loop, okay, one loop. So actually you can take this as we can write that first and then use the polar curve, substitute the r, okay, and then solve the integral. Okay. You can solve this as it is, or remember that this is symmetrical, right? So we could also think from 0 to pi over 4 and then multiply by 2. Okay? So we can take that symmetry. So we could take this from here. Okay, so due to the symmetry, then area is from 0 to pi over 4, half, forgot to multiply by 2. So area is 2 multiplied by half, and then cos squared 2 theta d theta. Okay. And still, how to solve this? We have a squared trigonometric cosine. How to solve this? The basic idea. What's the basic idea? Anyone remember how to solve this? You're very honest. Anyone remember how to solve this? Change to
Second.
yeah, that double angle formula. So this is, I think, my suggestion for all sine squared or cosine squared, change to double angle formula. Okay. So let me rewrite the formula for you. Okay. Just remember that we have this formula, right? and we can rewrite this as or. Okay, so it depends on what we have. We have cosine squared, so this is what we have. So we are going to develop into cosine with the double angle. Okay, because when we have this cosine 2 theta, sine 2 theta, or anything that sine or cosine without any square, we can integrate easily, right? We can integrate easily. Okay, so that's why we can use this part here. And since it's 2, it's become 4, right? Become doubled. So we can imagine that this is the formulations. Okay, we are using that. So this is cancelled. So area is another half, okay, from that particular exchange. So this is 0, pi over 4. This will be cos 4 theta plus 1 d theta. And integrate as usual. Cos sine 4 theta becomes sine 4 theta divided by 4. Okay. And plus theta. And evaluate from 0 to pi over 4. The sine part will be 0, right? 0. And theta, pi over 4 multiplied by half, it's pi over 8. So I think I will give you another part in calculus, like arc length, the tangent as well, and then after that we can review all in the exercise. Okay? We can review, okay, probably tomorrow, okay, with more review. Especially for the area, for the polar region, we need more practice, more review. Okay. Any questions on this example? Any questions? Any question? You don't know what to ask? Because you maybe not really understand what it is. Yeah, but we will have more exercise tomorrow, I think, for this part. I will give you another sections first. So we are start from the area, and then arc length, and then tangent. Because the tangent part is actually pretty similar to the parametric. Okay. A little bit different, but at the end it's similar. So let's go through the arc length. Okay, remember that we have relations between the Cartesian and polar. We can rewrite this. Okay. And we can rewrite this as the r as a function. So x can be rewrite as function theta, cosine theta. And y also, you can exchange the r into the functions. Okay, to find the length, so let's start with develop that r is function of theta, and the theta is from A to B. And as usual, as we did in parametric, okay, we are going to start with finding the first derivative for each x and y. This will be dr dt cosine theta, or let me start with the from x. We'll write x equal r cosine theta. Okay, because now r is not a fixed or not a constant, it's a variable. Theta also a variable. Okay, so when we are going to find dx over d theta, then we are going to take the product rule. Okay, so this will be a variable, this is also a variable. Okay, so we are going to take the product rule. So the first thing, taking the product rule, and then plus r, and the cosine become negative sign, so it's become negative. So negative r sine theta. Okay, and y, taking the another product rule, and it's become cosine plus r cosine theta. Okay, now taking the square. So if we take the square from both of this, why we need to take the square? Because in the arc length you need both squared, right? So take the square for both dx dt and dy dt. Okay. And then remember, in parametric, we have the arc length in this structure, right? So we need to plus both of them. So let's do that. So let's plus these two. And try to solve each one of them. So we need to take the squared . Okay, and then my minus 2r dr d theta sine theta cos theta, right? And then plus r squared sine squared theta, and then plus and then this will be dr d theta squared sine squared theta plus 2r dr over d theta sine theta cos theta plus r squared cosine squared theta. Okay, I think pretty good. Okay, notice that we can cancel this, right? And then we can take this and this, also this and this, because sine squared plus cosine squared is 1, right? So we can take that. And then we can make it r squared. Okay. So this will be our dx d theta squared plus. But we need to make into the square root, right? So it's pretty much the same as the parametric, but what we are going to change is changing all into the polar, into r theta. So usually in parametric, let's say the parametric now is theta, okay? Okay. We have learned this before, right? The t with t, okay, the same thing. Now in polar, where r is function of theta and theta is from a to b, now the arc length becomes r squared plus dr over d theta squared d theta. Okay. That's for the arc length. Okay. And lastly, the tangent. So I will give you the area, arc length, tangent. We will review tomorrow. Okay? We will review tomorrow and give you more practice. If you want, you could try to develop your own writings. In parametric, you have this. The difference in polar is we are going to evaluate these two in terms of a polar, which is x is r cosine theta, y is r sine theta. And the same thing for tangent. we start from our conversion xy. We find dy over dx through that dx d theta dy d theta. Pretty similar. But what we are going to do is we just change from the parametric that we have to polar. And how to solve in one question? Sometimes you can solve directly using this parametric, it's a regular parametric, or you want to change the polar, it's also okay. Depends. It depends. Okay, let me give you the last notes sections. That is about tangents. So similarly, we are going to start with writing the conversion for each x and y in polar. And then if we want to find the tangent dy over dx, we are going to find dy over d theta and dx over d theta, right? And we get that from the product rule that we have before. Okay? Exactly the same. So we are just plugging in all the information for y. This will be plus r cos theta. And for x, okay. And that's it. And of course, very similar to parametric, we could also find the horizontal tangent. Where the dy d theta is 0, or the vertical tangent. Where the dx d theta is 0. Oh, this is another dx d theta 0. And if we really careful on looking at the tangent line, that dy over dx is actually our tangent theta. Okay. If dr d theta is not equal to 0. This is tangent line. Tangent lines at the pole. So one possible questions from the tangent, perhaps first is finding the derivative, or maybe the second derivative, and also finding the horizontal tangent, vertical tangent. If you see from the polar curves that maybe you look, it has maybe cardioid or any any forms, any curve, you will see that we are going to evaluate from the polar axis, from the zero, angle 0, and we rotate, and maybe we are going to see some of the tangent, right? Some of the tangent, the vertical, the horizontal, and perhaps we need to find when the curve get the horizontal tangent or vertical tangent. Okay, well, that's typical questions also for tangent. Okay, aside from finding the dy dx. This is if we need to find the tangent line at the pole. Tangent line at the pole. Okay, I think that's it for today's class. Okay, so we developed the area, the arc length, and the tangent. I think the more parts that you need to emphasize, I think the area. I think that's the most confusing one. I agree that it's confusing, especially when you need to draw the curve to find the intersection first. And imagine that if you have the polar curve and you have another polar. For example, maybe you have this, and you have also this, and you need to find this. That's pretty challenging. And I think if you read the exercise, you will see some of the questions is like this. Yeah, but we can try. We can try. So tomorrow, I think we can try to solve some of the problems. Perhaps 3-4 exercise for tomorrow. And the other sections in the chapter 10, I think I will skip. So I will just up until the calculus in polar. So no need for conic sections or the conic in polars. We can skip the 2 of the sections. So that's for today's class. Is there any questions first? Any questions? I think as I mentioned earlier, probably next week we will have a quiz. Okay. Chapter 8 and 10. Okay. Then as usual, we go to here. And we are going to have another feedback. Anyway, what subject what department you are going to take? Is it mechanical or chemical or civil construction or material science? Anyone? Natural science? Still not sure? Still not sure? Mechanical or civil? Mechanical. I think for you guys maybe mechanical, right? No, not sure. Not sure. Okay. Please take the subject or the department, not because you know you will get a high salary, blah blah blah. It's not really that matter. Of course it's matter, but it's not necessarily the things that you need to consider of. You need to consider also the other things. But that will be maybe another talk. Okay, I think we can start. Okay, any comments on today's lecture? Confusing? I think confusing on the area. On the area of the curve. Okay, good, thank you. Thomas answer. Okay, confused, sleepy, yeah. Worse, okay. Sleepy. Yeah, early morning class, very sleepy. What are you guys bullying each other. Confused, okay. This exercise answer. Okay. Yeah, handsome, handsome. Exercise, you mean the last exercise, right? The last exercise? I think I can provide that. Not understand? Okay. Maybe need to take time to understand. Okay. Okay, let's start. Okay. The first question, I think only one. I think only one question for today's. And hopefully there will be no interventions. So let's start. 3, 2, 1, go. Very small if you see on this screen. I think you need to look on your phone to get the exact words. I think too small if you read from here. Maybe look on your phone. Let me help you to write the question. Maybe here. The questions. Find the surface area. So surface area on this x, a cosine cube theta, y is a sine cube theta. Theta is from 0 to pi over 2. Rotate about x-axis. So remember, if you rotate above x-axis, if you rotate this is rotations, right? And you need to imagine what will be the radius. Okay? What will be the radius? Oh, 10 students submitted? Okay, good. I don't know whether it's just like,
test.
yeah. Okay, but I think you need to derive these two, right? Derive this x and y because you need to take it into the arc length also, right? The L, right? And rotate about x, which means the radius is here, right? Radius is y. So 2 pi y. And then you need to take this into the square root and dx d theta squared plus dy d theta squared, right? But you need to derive first and then square. Derive with respect to here the parametric is theta. Parametric is theta. And then at the end, plug in 0 and pi over 2. And a is still there. A is just a constant. A is still there here. I think you can take a guess and narrowing the answer. Okay, if you can take the derivative, this will be going to the front. Chain rule, don't forget. Chain rule. We are still just using the parametric. Just using the parametric. Although the question is in theta, we are not yet in polar. This is still parametric. The surface either 2 pi x or 2 pi y depends on the rotation. 2 pi x dl, 2 pi y dl, right? dl is the same. Square root of that derivative squared, okay, plus other derivative. everyone has voted. Again? Wow, what's happened? Does that mean the internet refresh? Really sorry about that. Okay. Okay, congrats. Okay, perhaps tomorrow I will take the computer. I think maybe unstable connection on my iPad. Okay, sorry, sorry about that. Okay, that will